Hello everyone. So welcome to this lecture on electromagnetic induction. In this lecture we will talk about mutual induction. However, just as a recap, let's recall what we learned regarding self-inductance. We have learned that self-inductance is the property of an electric circuit by virtue of which uh, it may resist any change of magnetic flux linked with the coil or linked with the circuit. So basically, if the magnetic flux linked with a circuit or a coil changes, in that case an EMF is induced, and the EMF is induced in such a direction so as to oppose the original direction of the current. I mean, whatever current that will be induced in the circuit because of the induced EMF, that will oppose the original current which has actually produced it. So that's a very brief recap of the self-induction. In the mutual inductance case, just one thing to remember, that in the self-inductance we have got only one circuit where there is a coil which is being wrapped. In the mutual induction we have got two different circuits, and rather two different coils, and one coil is attached to a voltage source which is giving a change to the current, and the other circuit is absolutely in a resting position with no voltage sources connected. However, because the current in one circuit is changing, the magnetic flux associated with both these circuits will change, and as a result of which there will be an EMF induced in the second coil and it will give rise to a current. However, the current will once again oppose the original direction of the current. So let's try to understand this in a sequential manner. So as a part of definition, mutual inductance, as you can see over here, the mutual induction is the property of two coils by virtue of which each opposes any change in the strength of current flowing through the other coil. So you can see here there are two coils. This is a coil 1 as already has been depicted, and this is coil 2. Now in coil 1 we have connected an AC source. Let's consider this an AC source. Why AC source? Because AC sources are capable of giving you a variation of current with time, because in AC source, you know what do you mean by AC, alternating current? That means suppose this is time axis and this is current axis. In that case the current of an AC source will vary like this. So we are not bothered about this particular part. We are only bothered about this part where current increases, attains a maximum, and then again decreases to zero. All right. So in the next instance, which has been shaded, I mean this particular part, here the current will flow in opposite direction. So let's consider this first case where the current increases, attains a maximum. In this case, what will happen? This current I1, which is flowing through the circuit 1 or coil 1, is changing with time, or rather it is increasing with time. So as there is a rise in current through this particular coil, there will be a magnetic flux which is linked with this coil, which will change basically, rather which will also increase because I1 or the current is increasing. Now since this circuit, which is circuit 2 or coil 2, this is nearby to this coil 1, so that is why these magnetic fluxes will also flow through coil 2. And as a result, since the magnetic flux linked with coil 1 is increasing, the magnetic flux linked with coil 2 will also increase. As a result of this, there will be an EMF induced in this particular coil, that is coil 2, and because of that induced EMF we will see a current flowing through that circuit or coil, and that will be shown by this galvanometer which is connected to this circuit. Now forget about here the direction of galvanometer which is showing right hand direction or left hand direction. Just remember one thing, that the current which will be induced in the second coil, that will always oppose the current which is flowing in the first circuit. That means it will flow in an opposite direction, means it will give an anti-magnetic field to the original magnetic field. So this whole thing has been briefly discussed in these particular lines on this slide. So if you just go through these lines, you can easily understand. So one thing just you have to remember, that in self-induction, you have got one single coil through which current is changing, and as a consequence the magnetic flux linked with that particular coil is changing, and an EMF is induced in that same coil itself. But in mutual induction you have got two different coils. In one coil you are changing the current, and the effect is getting produced in another circuit or another coil. All right, that means induced EMF and induced current is getting produced in the other coil. Don't think that since I have got here two coils and current is flowing through one particular coil, there is a lack of self inductance in the coil 1. No, Self-induction will also be there in association with the or in addition with the mutual induction. All right. So we are not here discussing about the self-induction because we already have separately talked about it. So in this particular lecture, we will only be concerned with mutual induction. Self-induction will also be associated with coil 1. So, but that's a separate issue. We will not talk about that. We are concerned with how exactly the presence of coil 1 is affecting the coil 2. All right. This is, by the way, vice versa in the sense, if you connect the alternating current source to coil 2 and change the current in coil 2, same effect you will see even in coil 1. So that means mutual induction is mutual in true sense. That means it doesn't depend or it doesn't have a preference over coil 1 or coil 2. It only depends on the presence of two coils, and if the current in one coil is changed, the effect will be observed in another coil. All right. So this is all about mutual induction. A coefficient of mutual induction. This is quite similar to the coefficient of self-induction that we have derived earlier. But in this case, we will consider two coils instead of one single coil. So here let's consider this P and Q be the two required coils which are mutually connected and whose coefficient of mutual induction be M. So let us go through line by line. So let us consider two coils P and Q. Now if there is any change in current in P, an EMF is induced in the coil Q and vice versa. That means if you somehow connect this with an AC source of current and change the current, or rather you have got di dt, which is the rate of change of current is positive, that is current is increasing with time. In that case the effect will be observed in Q. That means an EMF E will be produced in Q. All right. And vice versa, that means if you connect the AC source to Q, similarly Q current will change and there will be an EMF produced in P. This is quite similar or quite equivalent of each other, right? So if I be the current flowing through the coil P, then magnetic flux through Q is given by phi is directly proportional to I. That means the magnetic flux linked with the coil Q changes. All right. By the way, so since there is a proportional signs, and if you want to remove this proportionality, in that case you have to put a constant of proportionality, which we have put in this case M. So if you just take a time derivative on both the sides, then you will get d phi dt, that's equal to M di dt. Why? Because M is a constant, so it will come out of the derivative. Now we know by Faraday's law that E, the EMF induced, is equal to d phi dt minus, by the way. So in that case what will happen? D phi dt, that should be equal to minus of E. So that's exactly what I have written here. Or I can write E is equal to minus of M di dt. Fine. Here M is a constant which is known as the coefficient of mutual induction. If I consider this quantity di dt to be is equal to 1 ampere per second, by the way, then E is equal to minus of M. So thus the coefficient of mutual induction between two circuits is numerically equal to the induced EMF in one circuit when the rate of change of current in other circuit is unity. That means whenever we talked about self-induction, remember in self-induction also we got similar relationship, that E is equal to minus of L di dt. In that case also we produce same thing, di dt if it is equal to 1, in that case E is equal to minus of L, but in that case we were talking only about one single circuit, but here we are talking about two different circuits. So the definition will change a bit, and how the changes that the coefficient of mutual induction is numerically equal to the EMF induced in one circuit when the rate of change of current in another circuit is unity. Clear? So let's go ahead and let us try to find the mutual induction of a long solenoid. So mutual induction of a long solenoid, in this case two solenoids are there, one is wrapped inside the other. So here you can see in this picture, let's consider the coil which is a bigger coil, you can say that's to be primary coil P, and the coil which is wrapped inside, that let us call it to be secondary coil S. So let us consider two coaxial solenoids PP and SS. The coil P may be called as the primary and the coil S may be called as the secondary. Alright. So let N1 be the number of turns of the primary solenoid and n to be the number of turns of the secondary solenoid. That means this particular solenoid, it has got n1 numbers of turns, and this solenoid has got n2 numbers of turns. So not necessary that n1 and n2 has to be equal. They may be different, rather n2 may be less than n1. So some kind of a relationship are there. I mean, n1 and n2 are different entities. Let A be the area of cross section of the solenoid. So in this case, I have not considered two different area of cross section for the coils, but rather we have considered that both the coils have got same area of cross section A, and let L, small l, basically be the length of the primary coil. That means this is the primary coil which starts from there, ends here. So this is the length of the primary coil. Now let current flowing through the primary coil be I. So in that case, what will be the magnetic field inside the primary, or so to say the secondary? I mean somewhere within the solenoid. That is already, we know it is given by mu naught Ni by L, but instead of N I will write N1. Why? Because primary has got N1 numbers of turns. So I will be writing B is equal to mu naught N1I by L, where mu naught is the permeability of the core material. Or in this case, we have considered the core material to be air, so we are considering the permeability of air medium. All right. Next, the magnetic flux through each turn of the secondary in that case. Now, why there will be a magnetic flux through the secondary coil? Because you are passing on a current through primary coil, which is given, which is basically giving you some kind of magnetic field lines. Basically, magnetic field line, suppose it is coming out like this. This is the northern side, and this is the southern side through which magnetic field lines are entering. Now, in that case, these particular magnetic field lines will also pass through the secondary. Since we are talking about mutual induction, so we will be passing current through one coil and getting the effect in another coil. So we are passing the current through primary coil and we are interested in watching the effect in secondary coil. So that is why I am considering the flux through secondary. All right. So now secondary coil has n2 numbers of turns. But let us first find what is the flux through each single turn of the secondary coil. So in that case, that is given by the product of the magnetic field and the area of the secondary, because we have considered here secondary and primary to have the same area of cross section. So area remains same. So B into A. So that's equal to given by mu naught N1I by L. So everything remains same, just A comes here extra. Now this is what? This is the flux through one single turn. Flux through one single turn of the secondary coil. All right. Now secondary has got n2 numbers of turns. So what will be the total flux through the secondary? That will be simply given by, say, phi b, that's equal to phi into n2. So if you just put the values of phi over here, you are going to get mu naught n1 into Ia by L. So again, we know that total flux through any coil in case of mutual induction, that is given by phi is equal to, or phi b is equal to m into I. So if you just compare these two relations, you are going to get m, the value of m, to be mu naught n1 into A upon L. So this is the value of the coefficient of mutual induction for the solenoid. All right. Or rather, we would like to say two solenoids wrapped inside. One is wrapped inside the other. All right. So that's all basically I had for today's class. In the next class, maybe we will talk about various other things on the mutual and self-induction. But one thing is important, that you understand the difference between mutual induction and self-induction in deep. So I think both these lectures on self-induction and mutual induction, if you have any confusion, please go through one more time through both these lectures, and before coming to mutual induction you should go and complete the lecture on self-induction. So once you understand self-induction better, then you are prepared for understanding the mutual induction. All right, so that's it basically I have for you. Thank you.